Welcome to the explainer. There's a kind of hidden language that describes pretty much everything in our universe. It's a language that can map out a simple walk in the park or the epic journey of a galaxy. Today, we're going to learn how to speak it.
So let's start with a question. What's the real difference between walking 5 kilometers and walking 5 kilometers north? Now, you might think, what's the big deal? But honestly, the answer to this one question unlocks one of the most powerful concepts in all of science. It's the key to understanding not just where you are, but how you got there and where you're headed next. So let's start at the beginning.
Before we can really describe the world, we first have to, measure it. But think about that. How do you measure something as huge as a football field or as tiny as a single sheet of paper? Well, physicists have a tool for just about every scale you can imagine.
We all know this one. We start with the good old ruler. It's perfect for getting super precise measurements of smaller things, right down to the millimeter. Simple, effective, and we've all used it.
But what about something way bigger? A ruler just isn't going to cut it for a whole sports field. That's when you bring out a tool like this trundle wheel. With every one of those satisfying clicks, it marks off another meter. It turns a massive measurement into basically a casual walk.
And check this out. This is just so clever. How do you measure the volume of something with a weird shape, like a rock? Easy. You just measure the water level, drop the rock in, and see how much the water rises. That difference? That's the rock's volume. It's a brilliant little trick called water displacement. Okay, so we can measure big things and we can measure small things. But what about the stuff that's, almost impossibly small, or something that happens incredibly fast? This is where physicists get really, really clever. Let me show you what I'm talking about. All right, here's a classic physics puzzle for you. A single sheet of paper is ridiculously thin, right? The markings on your ruler are probably thicker than the paper itself. So how in the world do you get an accurate measurement? The secret, and this is such a cool trick, is that you don't measure just one. You measure in bulk. Instead of trying to measure one impossibly thin sheet or one super fast swing of a pendulum, you measure a whole bunch of them at once. This one simple move dramatically shrinks your margin of error. So here's the game plan. You measure the thickness of a big stack, let's say 100 sheets of paper. Then you just divide that total measurement by 100. The exact same idea works for timing a pendulum. Time 10 full swings, then divide by 10. This simple bit of division gives you an amazingly precise value for just one sheet or just one swing. So we're getting pretty good at the how of measuring things accurately. But now things are about to get a little deeper. We have to ask a different kind of question. Is just getting a number ever really enough? And this quote just nails it, doesn't it? If someone tells you there's a treasure chest 100 paces away, that's useful, for sure. But if they tell you it's 100 paces away to the east, well, that's life-changing. You need more than just the number. You need the direction. In the world of physics, a quantity that's just a number, a size or an amount, has a special name. We call it a scalar. Think about things like distance or speed or mass. They all answer the question, how much? And that's it. But the moment you add a direction to that number, it becomes something else entirely. It's not a scalar anymore. Now we call it a vector. This is where things like displacement, velocity, and force come into play. They've got both a size and a direction. And that right there is the huge difference. Scalars answer just one question, how much? But vectors answer two questions, how much and which way? That single extra piece of information, which way, is a total game changer. It's what lets us describe the world with such amazing accuracy. This table lays it out perfectly with some great examples. And my favorite one here has to be mass versus weight. Your mass, that's the amount of stuff you're made of. It's a scalar. It's the same whether you're on Earth or on the moon. But your weight, that's a vector. It's the force of gravity pulling on you, and it always, always points in a very specific direction, down. Okay, so this whole vector thing isn't just some abstract theory, I promise. It's a seriously powerful tool that helps us map out and solve all sorts of real-world problems. Let's actually see how it works. And the way we draw them is just perfect. We use an arrow. Simple, right? The length of the arrow tells you the magnitude, so how big the quantity is. And the arrowhead, well, it literally points you in the right direction. All right,
Time to really put these vectors to the test. Let's imagine a hiker on a journey. They're going to make two simple movements, and we're going to use our new vector toolkit to figure out exactly where they end up. So here's the scenario. Our hiker walks 6 kilometers to the east. Then they make a turn and walk another 10 kilometers, this time due north. So the big question is, after all that walking, how far are they actually from where they started in a straight line, and in what exact direction? That straight line path is what we call their final displacement vector.
So, how do we find the length of that straight line path, the vector's magnitude? Well, if you look closely, the hiker's journey forms a perfect right-angled triangle. And that means we get to bust out an ancient but super powerful tool, Pythagoras' theorem. We just plug in the numbers, 6 squared plus 10 squared, find the square root of that, and bam, we get our answer. The hiker is about 11.7 kilometers away from their starting point. That's the magnitude. Pretty slick, right? But hold on, we're not done. That's just the how much. We still need the which way. To find the direction, we need to calculate the angle of their path. And for that, we can use a little bit of basic trigonometry. When we do the calculation, we get an angle of 59 degrees. So now we can say with total confidence, their final displacement is 11.7 kilometers at an angle of 59 degrees north of east. We have a perfect, complete description of their entire journey. And really, that's the heart of it all. Think about that. With just two simple ideas, scalars and vectors, we've unlocked a language that can describe motion anywhere in the universe. It works for a simple hike, and guess what? It also works for the orbits of planets and the paths of entire galaxies. It all just boils down to knowing two things, how much and which way. And that is the beautiful, simple power of the language of physics.